electrical system may have a ground loop, where an unintended electrical path exists between the electrical system ground and the earth. This can allow current to flow through a conductive path like a chain link fence, creating a shock hazard. As discovered, the wiring within the concrete light pole was shorted. This could have allowed current to leak into the concrete and metal inserts, which then traveled through the soil. Even if the light pole and fence are not physically connected, they can still interact through capacitive coupling. This is especially true in wet or conductive soil, where the capacitance between the two structures can provide a path for current to flow. If the light pole is carrying a large amount of current, it can create a magnetic field. This magnetic field can induce a voltage in the fence, creating a shock hazard. When high voltage is present, a difference in voltage can exist between the ground where someone is standing and the ground where the fault occurs. This difference in potential can create a step potential, where a person can be shocked by stepping from one area to another. Soil conductivity is a factor, and wet or conductive soil can provide a better path for current to flow, increasing the voltage. The closer the fence is to the light pole, the more likely it is to experience voltage. Taller light poles can create a stronger magnetic field, increasing the potential for inductive coupling. A longer fault path in the light pole wiring can increase the amount of current leaking into the ground. Mitigation measures include ensuring proper grounding and bonding of the electrical system, inspecting and repairing any faulty wiring or components, installing ground rods or other grounding devices near the fence to provide an alternative path for current to flow, insulating the fence from the ground using non-conductive materials, and using surge protection devices to limit voltage spikes that could damage equipment and create a shock hazard. In more detail, a ground loop occurs when there are two or more paths to ground in an electrical circuit, creating a loop. This can happen when equipment is grounded through both the grounding conductor of the electrical wiring and through a metallic connection to earth, such as a water pipe. The different ground potentials can cause current to flow through these paths, creating unwanted noise or even a shock hazard. Faulty wiring, such as damaged insulation or loose connections, can allow current to leak from a live conductor to ground. This leakage current can then flow through unintended paths, such as a metal fence, creating a shock hazard. Capacitive coupling occurs when two conductors are separated by an insulator, forming a capacitor. In this case, the light pole and the fence can act as conductors, with the soil acting as the insulator. When the light pole is energized, a voltage can be induced on the fence through capacitive coupling, even if there is no direct electrical connection between the two. Inductive coupling occurs when a changing magnetic field from one conductor induces a voltage in another conductor. In this case, the current flowing through the light pole can create a magnetic field that induces a voltage in the fence, especially if the fence is located close to the light pole. Step potential is the voltage difference between 2 points on the ground. When a fault occurs, such as a short circuit in the light pole, the ground potential near the fault can rise significantly. This can create a voltage difference between the ground where someone is standing and the ground where the fault occurred, potentially causing a shock if someone steps between these 2 points. Soil conductivity plays a significant role because the soil acts as a conductor, allowing current to flow from the light pole to the fence. Wet or conductive soil, such as soil with high salt content, provides a better path for current to flow, increasing the voltage at the fence. The closer the fence is to the light pole, the stronger the electric and magnetic fields that can induce a voltage on the fence. Taller light poles can carry more current and create stronger magnetic fields, increasing the potential for inductive coupling. A longer fault path in the light pole wiring can result in more current leaking into the ground, increasing the voltage at the fence. Proper grounding and bonding of the electrical system are essential for safety. Grounding provides a low impedance path for fault current to flow back to the source, allowing overcurrent protection devices to trip and energize the circuit. Bonding connects all metal parts of the electrical system together, ensuring that they are at the same potential, reducing the risk of electric shock. Inspecting and repairing any faulty wiring or components is crucial for preventing electrical hazards. This includes checking for damaged insulation, loose connections, and other signs of wear or damage. Ground rods or other grounding devices can provide an alternative path for current to flow, reducing the voltage at the fence. These devices should be installed near the fence and connected to the grounding system. Insulating the fence from the ground can help to prevent current from flowing through it. This can be done by using non-conductive materials such as plastic or rubber to support the fence posts. Surge protection devices can help to protect equipment from voltage spikes caused by lightning or other events. These devices can also help to reduce the risk of electric shock by limiting the voltage that can appear on the fence. To further elaborate on the specifics, firstly, ground loops are often created unintentionally and can be difficult to diagnose. They can occur when multiple pieces of equipment are connected to the same ground through different paths. For example, a lighting system and a fence might both be grounded to separate ground rods. If there is a potential difference between these ground rods, current will flow through the ground loop, potentially energizing the fence. Secondly, faulty wiring can manifest in various forms, including cracked or brittle insulation due to age or environmental factors, loose connections due to vibration or improper installation, and physical damage from rodents or accidental impacts. Regular inspection and maintenance are essential to identify and address these issues before they lead to dangerous situations. Thirdly, capacitive coupling is more pronounced at higher frequencies and in environments with high dielectric constants. The capacitance between the light pole and the fence depends on the distance between them, their surface area, and the properties of the soil. Wet soil significantly increases the capacitance due to the higher dielectric constant of water. Fourthly, inductive coupling is influenced by the geometry of the conductors and the frequency of the current. The closer the fence is to the light pole and the higher the frequency of the current, the greater the induced voltage. Shielding the conductors can reduce inductive coupling. Fifthly, step potential is a serious hazard in high voltage environments such as substations. The voltage gradient around a ground fault can be significant, and a person can be injured or killed by simply taking a step in the wrong direction. Grounding grids and equipotential bonding are used to minimize step potential in these areas. Sixthly, soil conductivity varies depending on the type of soil, its moisture content, and its temperature. Clay soils tend to be more conductive than sandy soils, and wet soils are more conductive than dry soils. Soil conductivity can be measured using a soil resistivity meter. Seventhly, the height of the light pole affects the strength of the electric and magnetic fields it generates. Taller poles can carry more current and create stronger fields, increasing the potential for both capacitive and inductive coupling. Eighthly, the length of the fault path in the light pole wiring determines the amount of current that can leak into the ground. A longer fault path provides more surface area for current to leak, increasing the voltage at the fence. Ninthly, proper grounding involves connecting all non-current carrying metal parts of the electrical system to a common ground point. This provides a lower impedance path for fault current to flow back to the source, allowing overcurrent protection devices to trip and de-energize the circuit. Grounding electrodes, such as ground rods, are used to connect the grounding system to the earth. And tenthly, bonding involves connecting all metal parts of the electrical system together to ensure that they are at the same potential. This reduces the risk of electric shock by preventing voltage differences from developing between different metal parts. Bonding conductors are used to connect metal enclosures, conduits, and equipment to the grounding system. Additional factors can also contribute to the problem. For instance, the presence of other buried utilities, such as water pipes or gas lines, can affect the flow of current through the ground and increase the voltage at the fence. The type of lighting used in the light poles can also play a role. Some types of lighting, such as high-intensity discharge HID lamps, can generate significant amounts of harmonic distortion, which can increase the potential for capacitive and inductive coupling. In addition to the mitigation measures already mentioned, other steps can be taken to reduce the risk of electric shock. These include installing ground fault circuit interrupters (GFCIs) to protect circuits that supply power to outdoor equipment, using insulated tools and equipment when working on electrical systems, and providing training to workers on electrical safety procedures. It is also important to regularly inspect and maintain the electrical system to identify and address any potential problems before they lead to dangerous situations. This includes checking for damaged insulation, loose connections, and other signs of wear or damage. If a person experiences an electric shock, it is important to seek medical attention immediately. Even a seemingly minor shock can cause serious health problems, such as heart arrhythmias or nerve damage. In summary, a combination of factors can contribute to a chain-link fence becoming electrified near faulty light poles. These factors include ground loops, faulty wiring, capacitive coupling, inductive coupling, step potential, soil conductivity, fence spacing, light pole height, and the length of the fault. By understanding these factors and taking appropriate mitigation measures, it is possible to reduce the risk of electric shock and ensure the safety of people and property.